Hello, today we are going to talk about finding the characteristics or the pieces of rational functions. So we are going to just find these before we start graphing. So we're going to find vertical asymptotes, horizontal asymptotes, slant asymptotes, x and y intercepts, and domain. I want to be clear that this separates going into all rational functions and not being limited to parent graphs. So there are slightly different rules that apply to parent graphs just because of the format of the equation. So moving forward, we want to use what we're going to talk about with these in regards to the characteristics of all rational functions. So to find a vertical asymptote, we are still going to do the same thing in which we are setting the denominator equal to 0. And we need to state these as equations. And then we're also going to write the domain because the domain is affected by our vertical asymptotes. So all we have to do is set the denominator equal to 0. So we're going to say x squared for this first one minus 5x minus 14 is equal to 0. We can factor that to be x minus 7 and x plus 2. And then we can say that this would be x equals 7 and x equals negative 2. So those two would be my vertical asymptotes. So we're going to have two vertical asymptotes in this case, which also happen to be our excluded values, which those are related. And then our domain is going to be all real numbers except for those two values. And so how we want to write that would be from negative infinity to the first one, so that'd be negative 2, with a parenthesis because we don't want to include negative 2, union negative 2 to the next one, union 7 to positive infinity. So that would be our domain because we are excluding those two values and making sure that they're using parentheses. Doing the same thing on the next one is we set the denominator equal to 0. And then we go to solve. We would say x squared is equal to negative 4. We would square root, and when you would get plus or minus 2i. Now, we need to recognize that imaginary numbers are not going to be excluded values because we always say our domain is based on the real number system and on the x-axis, and 2i is not on there. So we do not have any excluded values or vertical asymptotes. So for vertical asymptotes in this case, we would say none. And then that means that we don't have any excluded values in our domain, so our domain would be all real numbers. So this is kind of a special case when you get an imaginary that does not affect our vertical asymptotes. All right, moving on to horizontal asymptotes, is very important that you want to compare the degree of the numerator to the denominator. And this is all talking about how fast a function will grow because a higher degree function will grow much faster. And so that will kind of talk about any limiting factors and things like that. So if the degree of the numerator is greater than the degree of the denominator, then there's going to be no horizontal asymptote because the degree on top is going to continue to grow faster and faster. So there's no limiting horizontal asymptote. If the degree on the numerator is less than the degree of the denominator, then the degree on the bottom is growing much faster, and so we're going to approach 0. So we're going to have a horizontal asymptote of y equals 0. And then if the degrees are the same, then we would look at the leading coefficient of each polynomial, and then we would find the ratio between those or create the fraction of those. So looking at these, if we look at this first one, we have y equals 3x squared minus 2x over x plus 3. We're not doing anything with vertical asymptotes, we just want to find horizontal asymptotes. So looking at this, we can see that our degree on the top is going to be 2, and the degree on the bottom is going to be 1. So if the degree on top is larger, we are going to say for horizontal asymptotes, there would be none. For this one, we look at x to the third, so our degree here is to the third, and our degree here would be to the third. And so we want to look at leading coefficients. We have negative x cubed and 3x cubed. So our horizontal asymptote would be y equals negative 1/3, because that's the leading coefficient, negative 1 over 3. Looking at the next one, our degree on top here is, for x would be 1, and the degree here would be 2. So the degree on bottom is larger, and so we would say our horizontal asymptote, according to the last slide, would be y equals 0. The next one, we have x squared and x squared, so our degrees are the same. And so we would say leading coefficients for our horizontal asymptote would be y equals 5 over negative 1. So we could write that, or we could just say y equals negative 5. And that would be our horizontal asymptote. So if you look at the first one, when we don't have a horizontal asymptote, there is going to be an asymptote that's going to kind of be a boundary or how things happen, or end behavior more specifically. And so that's going to be called a slant asymptote. And it's a slant asymptote because it's not a horizontal asymptote. But it only occurs when there's no horizontal asymptote. And so when you have no horizontal asymptote, you're going to have a slant asymptote in this case. And this only occurs when the numerator degree is 1 larger than the denominator degree. And that's what we're going to discuss today. And how you find a slant asymptote is you want to divide the numerator by the denominator, and we want to ignore the remainder. So we don't really care about the remainder. We just want to find the equation of the line is going to be a linear equation for everything that we do, just because our degree of the numerator is going to be 1 larger than the denominator, and that creates a linear quotient. So if we have something like this where we have y equals x squared minus 2x plus 1 over x minus 4, our degree is 2, and our degree here would be 1. So for horizontal asymptote, we would say none, because the degree on top is larger. But for our slant asymptote, we do actually need to find this. And so if we can use synthetic division, we want to use synthetic division because that's going to be much more efficient. So we would use 4, and we would go into 8, negative 2, 1. So we bring down our 8, 4 times 8 is 32, we will get 30. And I really don't care, I would stop here at this point. Just for division purposes, we can say that 4 times 30 is 120, and we would get 121, but we really don't care. All we are looking for is y equals 8x plus 30. That is what we're looking for. We don't care about the remainder. Same thing for the next one. We have x to the third minus 9x plus 2 over x squared plus 3. We have squared and cubed, so cubed is larger, so we would have no horizontal asymptote. But we aren't able to use synthetic division, so we want to use long division for this. So x squared plus 5 goes into, and we can add an x if you want in there. I'm going to add a placeholder of 0x squared just to make things a little bit more easier to work with, minus 9x plus 2. And then we want to say leading term, so x squared into x to the third is going to go in x times. And so we would end up with x to the third. And then we have a 0x squared because there's technically a 0x squared in between those two. And then we would have plus 5x. We always want to subtract at this step. So we're really going to be subtracting this 5x. So we get 0x squared minus 14x. And then we bring down our plus 2. And then we want to say that x squared doesn't go into 0x squared because there's nothing there, so that will eventually kind of go away, and we have negative 14x. And x squared is too big for negative 14x, so we would just have y equals x, because the rest will be a remainder, and we don't care about the remainder. So anytime we have no horizontal asymptote, you will have a slant asymptote. The last information we need to find are your x and y intercepts. And so finding your x and y intercepts, you want to do the same thing as we always have. So for our x-intercepts, we want to plug in 0 for y. So we would say 0 equals 2x minus 6 over x minus 4. And then here we can cross multiply. This is like 0 over 1. We can solve this by saying 0 times x minus 4 is just going to be 0 is equal to 2x minus 6. We would add that over to get 6 equals 2x, and so we would get x equals 3. Making sure that we write our intercepts as ordered pairs, we would get 3, 0. So make sure that you take that extra step to write it as an ordered pair. For your y-intercept, we would say plug in 0 for x. So we have 2 times 0 plus minus 6 over 0 minus 4, and that's just going to give us negative 6 over negative 4, which is going to be 3 over 2. So we would get this as 0, 3 over 2 as our y-intercept, making sure we write it as an ordered pair. Look at the next one. G of x, again, x-intercept, we're plugging in 0 for y, or g of x in this case. And so we would say 0 is equal to x squared plus 9 over x squared minus 9. And we would cross multiply again, and we would get 0 equals x squared plus 9. And so we would get x equals plus or minus 3i when we solve that, which we should see that that does not cross our x-axis. So for x-intercepts, we would say none. So it's important with imaginaries that we're talking about a graph or an x and y axis. Zeros would be plus or minus 3i, but x-intercepts we would say none. And then for our y-intercept, we plug in 0 for y, x, I'm sorry. So g of 0 would be 0 squared plus 9 over 0 squared minus 9, which would just give us negative 9 over 9, which is negative 1. So we would get 0, negative 1. One important thing to point out is that we ended up getting to this step, which is our numerator set equal to 0. So we should be able to take that as that will always occur when we're solving for our x-intercepts or for our zeros in this case, or whichever case way we're trying to find. So we can just go ahead and get to that shortcut is what this bottom part is finding, is saying that for the x-intercepts, all we need to do is set the numerator equal to 0. And we can find our x-intercepts that way. So we're going to find some practice in the next few